Yeah, hi. First, I want to thank the organizers for giving me the opportunity to give a talk here. And yeah, I'm talking on harmonic weak mass forms associated to even weight newforms. So I'm going to start with saying what harmonic weak mass forms are and why people, and in particular I, am interested in them. So this is my first section. On harmonic weak mass forms. So throughout the talk, gamma will be a congruent subgroup of SL2Z. And K will be a positive integer. And we're going to look at spaces of modular forms. So here maybe I let L be, could also be in half integers. So I want ML to be just the usual space of modular forms of weight L for gamma. So I mean, if L is half integral, then we'll take a subgroup which has level 4n. And so these are just the usual holomorphic modular forms, holomorphic on the upper half plane and also holomorphic at the cusps. And SL is the space of cusp forms of weight L for gamma. And by this M shriek of L, I denote weakly holomorphic modular forms. So these are the ones that are allowed to have poles at cusps of finite order. Okay. Well, and so my motivation to study modular forms is usually, not all the time, but usually that they serve as generating functions of some kind of arithmetic function or function that is of interest to anyone in number theory or physics or so on. Okay, and then almost 20, or maybe more than 20 years ago, Jan Brunier, who's also here, and Jens Funke introduced a new space of modular objects called harmonic weak mass forms. So what are these? These are also functions that live on the upper half plane. They're smooth on the upper half plane. And then these also have a weight and some group associated to them. So maybe we can also use L here. If this function f satisfies the following three properties. So the first one is now, so the usual modular forms, they're just holomorphic on the upper half plane, and we replace this condition by being harmonic. So these are annihilated by a weighted Laplace operator. So here I split a complex variable into a real part denoted by x and imaginary part denoted by y. And then they're Oh yeah, thank you. Yeah, thank you. Always. Yeah, okay, now it's correct. And these just transform the same way as modular forms, cusp forms, and weakly holomorphic modular forms. So I don't write down the transformation behavior, but just f transforms like a modular form of weight L for my congruent subgroup gamma. And then these things are supposed to have exponential growth at the cusp. This is why they're called weak. So those of you who know the usual definition of Maass forms, which originally was given by Maass, those have polynomial growth at cusp, and they have an arbitrary eigenvalue for the Laplace operator. So this is why they're called weak for the weak growth or weaker growth, and harmonic for being harmonic. Yeah. Well, and I guess the first question is that a reasonable space, right? So is it non-empty? Are there any cool examples having some meaning? So Jan and Jens introduced these more in like a setting where they were using Borchert's products. And so these serve as a nice input for Borchert's products because they have, I mean, Borchert's used weakly holomorphic modular forms as inputs, and then these kind of have more space for being singular, right, at cusp. And around the same time, Sanders-Weggers wrote his PhD thesis on Ramanujan's Mach theta function. So there's this miraculous story about Ramanujan, who wrote down this very weird Q series and claimed that their Mach theta and theta function for him was a modular form. So what he said was they mimic the behavior, the modular transformation behavior. And no one could find, I mean, then this was in the last notebook and all the stories and was lost, whatever, and so on. But no one could find out, even when it was discovered, what he meant. Like, no one really saw how they transform. And they always had this ugly kind of thing appearing when you just plugged in just the matrix of SL to Z. And then Sanders-Weggers found out that these things are parts of such harmonic weak Maass forms. So just as usual modular forms, you can use the fact that they're invariant under, the T matrix, so they're one periodic, so they have some kind of Fourier expansion. And then you use the differential equations given by the first condition here, and you use that you can determine the growth at the cusp. And then you can find out that these have a Fourier expansion of the following type. They split into a holomorphic part and a non-holomorphic part. And the non-holomorphic part, I mean, this comes from kind of analyzing the eigenfunctions for the Laplacian. It has an incomplete gamma function. And the holomorphic part is just, looks like the Fourier expansion of a weakly holomorphic modular form. So you have some poles of finite order. And we'll later see that this is also related to some, one of these classical objects. But so Sanders-Weggers, he basically wrote down a completion of this series Ramanujan wrote down, where he took Ramanujan's Mach theta functions as the holomorphic parts, not using this terminology, which was kind of developed, I guess, at the same time, and kind of wrote down for each of these Mach theta functions a non-holomorphic part. And then the resulting object just transforms like a modular form. And this is somehow why these objects get very popular at once, because they give a theoretical framework for these mysterious functions of Ramanujan. Okay, and something is also very special about Ramanujan's Mach theta functions. They have integral Fourier coefficients. So these things here are integral. I mean, for modular forms, this is one of the first things you learn. It has, like, the vector space of modular forms of fixed weight has a basis with integral Fourier coefficients. And here, this property doesn't come for free. I mean, there's this one example of these Mach theta functions of Ramanujan, and they have these coefficients have a combinatorial interpretation, and so they're integral. But other than that, these things seem to be kind of out of the control in the sense that they are all transcendental. And today I want to talk in part about some situations where you can gain some kind of control on these coefficients. And I said before, this kind of looks like, or it does look like the Fourier expansion of a weakly holomorphic modular form. This does not, but it turns out that this can be related to cusp forms by using a certain differential operator, namely the psi operator. So if we call this space here H sub L, then there is an operator, differential operator, given by 2 times I, and then the imaginary part to the L's power, and then you take d dz bar of a harmonic Maass form, and that maps the space of harmonic weak Maass forms of weight k to the space of cusp forms of weight, or maybe I use L again, to the space of cusp forms of weight 2 minus L. And this gives an injective map. Ja, danke. Warum komme ich jetzt? Okay. Yeah. I don't know why I confused these. Okay. Because our questions I want to ask don't make sense. Thank you. No, I don't even have it correct in my notes. I don't know. It's late, I guess. And it's before dinner. So maybe that's why. Okay. Yeah. So, surjective map. I mean, cusp forms we know kind of well, but I mean, we not too well. Take, for instance, I think, so the first cusp form, like of lowest weight, the delta function, we don't even know that the coefficients are non-vanishing, right? That's Lehmann's conjecture. And I think that's kind of crazy, given that modular forms have been studied for I don't know how many years. So the first question, if you know this map, is somehow given a cusp form G, and let's say S2 minus L, is there a nice preimage of G? Well, and I mean, you can do kind of generic things and take generators like Poincaré series here and kind of identify the correct Poincaré series on this side, but this is maybe not so interesting. I mean, it is interesting, but it's not so interesting when you think about your cusp form being special at some, like, for example, I guess what a special cusp form for me is some cusp form that comes from an elliptic curve or SCM or Hecke cusp form. And then the second question I want to kind of address today, if such a preimage exists, what can we say about its coefficients? So in particular regarding algebraicity. Okay, and so here's one restriction here is kind of, so this part is the one that the psi operator sees, right? I mean, you just pretty much throw the psi operator on this. This is holomorphic, just goes to 0. This survives, and it just gives you the Fourier expansion of a cusp form. So this is not the coefficient we want to look at, because that's the coefficient in the cusp form, basically, up to some constants. So whenever I ask this question, what can we say about the coefficients? I mean the coefficients of the holomorphic part. Okay. So now I'm confused. That is one of my things. Yeah. Okay. So I want to address the first question first. And in the special situation when G comes from an elliptic curve. So let's say question 1 for K, for F, for G in S2. So if we have an elliptic curve over the rationals, by the modularity theorem, there is a cusp form, or more precisely, a new form of weight 2, also with rational coefficients associated to it. So here I wrote down the group gamma, and then the conductor kind of tells you what kind of elliptic curve it is that it's related to. And this has rational Fourier coefficients. Okay. And in that special case, we can construct a natural, or one of my colleagues, he always says nature is not taking over in mathematics, so I started to talk about distinguished preimages, but somehow I guess it's also a bit natural maybe. And you can construct it using Weierstrass's elliptic functions, which is, yeah, kind of very basic and easy and very cool, I think. So over the complex numbers, E is isomorphic to C modulo the period lattice of G, and I kind of don't want to write lambda G the entire time, but I need a second variable in the upper half plane. So I write lambda G equal to lambda tau, and this is Z tau plus Z. And then we have, I guess, three Weierstrass functions hanging out. The sigma function, the p function, and the zeta function. And for the construction of this harmonic mass form, we need the zeta function. But it's kind of useful to construct it via the sigma function. So the classical sigma function is just z times the product here. And then you take the product over all lattice elements, not the 0 one. And then it's just this thing you learn in, I guess, complex analysis 2. And what's not, so for this basic construction, it's not crucial, but to generalize this construction, a crucial thing to note is that the sigma function is related to the classical Jacobi theta function. So you can write it as the exponential. Eta of 1 is one of the quasi-periods, and then you divide by essentially the cube of the eta function evaluated at tau, and then here the classical Jacobi theta function appears. So the one which has weight 1/2 and index 1/2. Okay. And now this Weierstrass zeta function is given by the logarithmic derivative of the sigma function. okay, so kind of going back at what we want to have. So we start with something of weight 2, so L is 0. So we want something of weight 0. Weight 0, kind of, I mean, not thinking about modularity, but some lattice function would mean lattice invariant. This is not lattice invariant, right? So kind of a problem, which can be resolved. Okay, so there is a completion already given by Weierstrass, completion in the sense that you force this to be lattice invariant, and it's given by adding basically a multiple of z and one of the complex conjugate of z. So this is, yeah, I guess the first one is due to Weierstrass. Not Weierstrass, Eisenstein. And then there are different ways of kind of constructing this thing. A couple of proofs, one by Donzaghi. So you take just the Weierstrass zeta function, and you add z times the evaluation of G2 star at tau. So G2 star is the usual weight 2 Eisenstein series minus pi over the imaginary part of tau. And then you also add or subtract a multiple of the complex conjugate of z, namely pi, and then you divide by the volume of a fundamental parallelogram, of the lattice gamma of tau. Okay, and this now is lattice invariant, but we want something modular, so we kind of want to introduce the action of the modular group, and we want that our function under the Xi operator maps to the cusp form we started with. And so kind of this tells us maybe we want to take the antiderivative, right, of the cusp form. And this is also a well-known thing, namely the Eichler integral. So this is also an object which is well studied in the world of modular forms. So you take the holomorphic Eichler integral. And okay, this is also, I mean, this now at least gives you that whenever you take the Xi operator, so maybe it's mainly just the derivative of this thing, complex conjugation appears so many times that it goes away, or doesn't play a role anymore, you map to the right object. But you don't know if it's, so it has to be invariant under the action, the modular action of the modular group. And this is exactly what the Eichler integral does. If you consider the Eichler integral of gamma tau, this is just itself modulo the lattice. So you plug something into this function, which is lattice invariant, apply the action of the modular group, and then the kind of error to modularity is an element of the lattice, so it doesn't play a role in your lattice invariant function. So you kind of were done and constructed the correct object. The noise is not so great. And so who came up with this idea first, but only in a special, oh, I think that's gone, in a special case was Pavel Grzhy. And then did this quite a while ago, together with Michael Griffin, Ken Ono, and Larry Rowland. We kind of generalized this to cover more cases. We showed that if you define the function omega or wg of tau to be this completed Weierstrass zeta function evaluated at the Eichler integral of g, then this is a harmonic weak mass form of weight 0, which might have poles on the upper half plane. But there's also a construction that gives you a way to remove these poles. And, I mean, that's the crucial one. It gives you a natural preimage of the cusp from G you started with. Okay. Well, and I think we proved this in like 2013 or 14, I don't remember, so it's been a while. And, well, I guess the questions how to generalize this are very obvious. What if you do change the weight, or what happens if you change the fields of coefficients? So, right, you leave Q and go to a number field, or you look at a cusp form of weight 2K and want to look for a preimage. Maybe because I raised the second question kind of at the same point, here you can't really get a hold on the coefficients of this thing. I mean, you can compute them very nicely, but it's not that they're all algebraic or something. They're kind of random. Just in case if you have a CM form, then you have more general results telling you that the coefficients are algebraic. And one nice thing is always when you compute these things and then you see that they are really algebraic when someone else's theorem tells you they should be. So it's kind of nice to see that results match. But this is more kind of a nice construction and a good, easy way to numerically compute coefficients here. Okay. But more recently, I finally kind of, after getting a child, changing my job a couple of times, and COVID, finished with the generalization to both cases. One, if you leave the world where this thing is defined over Q but still has weight 2, and the other one where you stay with Q but change to higher even weights. And the key thing is, so maybe I did this. The key idea or key observation is here. So you can always, I mean, classically you construct the zeta function using the Weierstrass P function, right? And doing it that way, you don't really, like you can't generalize this construction. There's no modular form or modular object, but here there is one. If you use it, like if you define the zeta function as the logarithmic derivative of the sigma function, and before write the sigma function as some multiple of the Jacobi theta function, you kind of see where you can change things, right? Namely via constructing a more general object here, and then there are also, I mean, known constructions for, at least for the higher weight, that's Kuga, I think it's due to Shimura maybe, to define a Eichler integral, which then is valued in some symmetric power representation. So the first key observation is that the zeta function is the logarithmic derivative of the sigma function, and this is almost right up to constants and so on, something like the derivative of the classical Jacobi zeta function divided by itself. And then one needs to notice, and I think it was Larry Rowan that wrote this all down for the classical case, that it's not really the right thing to take a derivative here, but instead kind of use this rich theory of weight-changing differential operators you have in the world of modular forms. And then you can replace this kind of by the right weight-changing operator. And for Jacobi forms, you really do know what they do with the weight and with the index. And you know you somehow have to arrive at index 0 to get something lattice invariant. And this is also like the key for all generalizations. So instead of ddz or del del z, we consider a canonical raising operator on Jacobi forms. Okay. So So this kind of boils it down to finding kind of the right replacements at every step. So I guess the first things, I mean, you don't have an elliptic curve anymore, but so what? You have some kind of component of the modular curve. You still have period lattices. I mean, these are very naturally defined. And then you kind of have to make, like you have to find the correct theta replacement of the theta function. So so I do maybe 3a. If we still have y2, but now the coefficients of the cusp forms are in a number field, then instead of the Jacobi theta function, you have to take a Reman theta function, just the very classical one. Maybe write it this way. The most classical one that gives you a Siegel modular form. So now we pass from elliptic functions to abelian functions. And then you kind of have to make sense of what you plug in. And in that case, instead of looking at one cusp form, you look at the cusp form and all its Galois conjugates and plug in the corresponding vector of the Eichler integrals. So and here you kind of also have to look for the right the right raising operator. So theta hat is defined as some kind of raising operator. So again, explicitly given as a differential operator on theta divided by theta, where theta is now a Siegel modular form. And again, we were able to show that's joint work with, so I put it in quotation marks, the theorem, because I didn't write down enough details to make a real theorem out of it. But the completed theta function defined this way, and I mean these classical, so like all of these, let's say Weierstrass elliptic function things, apart from the completion, they were defined, I think, already by Klein. So this is really kind of old business. The only part that's new for this theta function or Weierstrass generalization business is to this completion part. So to make something lattice or abelian in that case. So you now plug in a vector here of Eichler integrals. this is again annihilated, has to be of weight 0. It's gamma invariant, and it maps to the thing you want under the xi operator. So now you have this vector, I call it G, so this is G itself and all its scalar conjugates, some kind of, and then here you have to multiply it. So the dot always means up to some constants, which are explicitly given, and this is some positive definite matrix, depending kind of on the size or the number of variables we work with. Okay. And then the weight 2k. So this was in the end kind of easy, and the weight 2k was a lot messier. And the reason is that this thing here is vector valued in the sense that it takes values in a symmetric power representation. And this thing then wants to be a Jacobi form in more than one variable, right? So you just take k. So if your cusp form has weight k, you want k minus 1 copies of z, or z's. And you want it to be invariant in each variable under the period lattice of the cusp form you start with. And then what we had to do was somehow, because if this thing is not scalar valued but valued in symmetric power representations, you get an additional action of the modular group on that representation, and that makes things very messy. So I'm not going to give the details, but just say that the generalization exists. So that also needed more authors, because there was more work, I guess, or we needed more courage to do it. So there is a construction of natural preimages of cusp forms of weight 2k now, so k was an integer, for gamma, some congruent subgroup with rational Fourier coefficients. The preimage is also not so nice in the sense that it takes values in a very weird representation space. So I'm criticizing my own result, but it's really, yeah, it's kind of not the thing you want, but I mean, in the end, we weren't able to do better, so that's what's there. Okay. All right, so everything I talked about until now, despite Ramanujan's mock theta functions, was about integral weight. So we took an integral weight cusp form and an integral weight preimage. What about half integral weights? So this is the last part of my talk, and this will now be more related to the Fourier coefficients of that preimage. So here we take, so the title of my talk is on harmonic weak mass forms associated to integral weight new forms. So we take a new form still of integral weight, but pass to the half integral world by using the Shimura-Shintani correspondence. So whenever you have something of integral weight, you can use the Shintani lift. So this can be explicitly written down by using the theory of theta liftings. And you can get a half integral weight form of weight k plus 1/2. Okay, and now we want to take a preimage here, which is then a harmonic weak mass form of weight 3/2 minus k. And so this is not chosen arbitrary, but you want it to, so aix-marseille, you want it to map to G normalized by the Petersen norm of G, and then this kind of makes it not unique, but a bit better. But here we don't really ask for a, let's say, canonical preimage, but we rather want to say something about the nature or the formula for these coefficients now. So the goal now is to describe the coefficients of the holomorphic part. Okay, and for k equal to 0, so still in the, sorry, not to 0, to 1, so the situation where, at least when this is defined over the rationals, you have this elliptic curve sitting in the background, then Jan showed that the coefficients of the holomorphic part, I just don't write this down anymore, are given as the quotient of two period integrals involving the canonical period and the period of a differential of the third kind. Okay, that's not as good as being algebraic, but it's way better than being transcendental, right? So it's kind of in between. In that case, when you have this relation via the Shimura-Shintani correspondence and so on to this integral weight cusp form, Jan Brunier and Ken Ono showed that you can relate or here, sorry, I wrote this down for rationality, but you can do it also for algebraicity. One can relate the rationality of the coefficients of the holomorphic part to the vanishing of the central L derivative of G. So, I mean, this is also, I guess, some interest in the context of the Burton-Svennon-Dyer formula, and you get this relation to the derivative by using the Gross-Zagier formula. So here we consider twisted L values. So we need a fundamental discriminant. So for simplicity, here we restrict to prime levels. So this P is the, is the level of G here. And you want this Legendre symbols to be 1. This kind of ensures that the functional equation gives you the right sign of L of G. And then this twisted L value vanishes if and only if you're in that diagram, the delta coefficient of F is a rational number. Well, and I mean, this doesn't happen very often. Okay, and what we were able to do last year with in joint work, so me, Jan, and Markus Schwagenscheid, is to generalize at least the first part, so this result here, to higher weight. So whenever you start with a cusp form, we were also able to explicitly construct. So here this result relies on the explicit construction of the differential of the third kind via a Borchertz lift. And we could generalize this also to higher weights. Here it's a bit not hopeless, I think, but this kind of, to get this relation to the critical L value, that's a lot harder because you kind of leave. So I mean, for Borchert's products, you always have these Hegner divisors in the game. But then, so I mean, Gross-Zagier formula is fine, the classical one. You have this Reman Theta height of two Hegner divisors. But if you change the weight of the cusp form and you go up, then you get Hegner cycles, and so somehow you have the Hegner divisor and the Hegner cycle, and the relation between those is not clear, at least not clear to me. So maybe I lose my, my last minutes, just give you an idea of what we did here. So, I mean, differentials of the third kind, so kind of compare this to the situation for 1. So you are in the modular curve, you take a divisor on the modular curve. So for the theorem, you just take a Hegner divisor on the modular curve. And then to this divisor, so here the restriction to any component of x has to have degree 0. And then you can use the Riemann period relations or whatever to show that there's a unique differential of the third kind. So something that has only poles of first order with integral residues. And then you just tell, like, its divisor, since it's only simple poles, you call it the residue divisor. And it gets unique by requiring that the real part of the pairing, so the real part of the integral against any cycle that avoids the poles of eta d is 0. Okay, and I mean, we don't, in that higher weight situation, we don't really have differentials anymore, but what we can do is we can identify these differentials of the third kind with meromorphic modular forms of weight 2. So maybe I kind of use this. So these can be identified with meromorphic modular forms of weight 2. By meromorphic modular form, I mean a modular form which is not holomorphic anymore on the upper half plane, but has poles, but it's still holomorphic at the cusp. And these we can, I mean, for differentials, no chance for higher weights, but for I mean, meromorphic modular forms, it doesn't hurt them to change the weight. So you can just talk about meromorphic modular forms of weight 2k. And instead of, so k greater 1, you look at meromorphic modular forms of weight 2k and poles of order k. Well, and I mean, these then have some Laurent expansion, or here now you'd like to consider kind of a modified Laurent expansion called elliptic expansion. Then there will be a leading coefficient, and using this leading coefficient and the poles, you can also define an analog of the residue divisor. And you can also define such a pairing here with closed geodesics and kind of redo everything, now not using the language of divisors, but the language of modular forms. And so I guess we all want to have dinner, so I'll just say and not write what I want to say. We are kind of able to construct also this, or to show the theoretical existence of such a unique differential associated to a residue divisor and so on, satisfying an analog of this condition. And then in a special situation where the divisor is a Hickner divisor, we can explicitly construct it using Borchert's products. And then the trick is somehow to modify the divisor and kind of weigh the divisor, or like a series of twisted divisors, by the coefficients of the principal part of this thing. And using this, one can then kind of give the result of this flavor and really give the coefficients of the holomorphic part here as a quotient of two period integrals, one involving these meromorphic modular forms which generalize differentials of the third kind. Okay, thank you.